Our second changemaker of the evening is Yee Wei Foong from the Department of Mining and Materials Engineering as well. Yee Wei is a second-year PhD student working under the supervision of Dr. Kirk Bevan. And he's going to talk to us tonight about how we can improve computer simulations of energy materials so that we can simulate how to build better batteries.
Thank you very much. How have our lives changed in the past few decades? Take a moment and look around us. It's not surprising to find that we have been relying heavily on electronic devices in our everyday life. Some of us rely on the wearable medical devices to keep track of our health so that the doctors can give a better treatment for us. And most of us rely on the portable electronics to work and also to connect with our dear friends and families. Not only we want to improve all these electronic devices to have a better quality of life, and there's another challenge that we are facing right now, is that we, as a great steward of this earth, would like all of these technologies to be green and sustainable for a better future. And that is why we see a trend in recent years that we would like to switch out the gasoline cars with electric vehicles. And also we would like to switch out the coal and gas power generators with solar farms and wind farms. And the question here is, why aren't they being applied widespread in our world right now? And the heart to this question is the energy storage devices that limits the potential of these technologies. And Marina already talked about the solar farm and how battery can help in that regard. So my talk will focus on electric vehicles. So if we take electric vehicles, for example, we know that for the gasoline car, if we fill out the tank, it's really easy for us to drive 600 miles without having to refuel again. But when the first electric vehicle came out with General Motors EV1 in 1996, you can see that it used the lead-acid battery, and it can only bring us about 50 to 80 miles per charge. This is not enough. And therefore, 7 years later, we developed the second generation of the battery using nickel metal hydride, which doubles the mileage for our electric vehicles. But still, it's not quite enough for us to catch up with the gasoline cars. And therefore, we have been waiting for 15 years. And today, we can see that lithium-ion batteries have been revolutionizing our electric vehicle industry. By using lithium-ion batteries, we can actually drive up to, on average, 300 miles per charge. This is very impressive, but still it's not quite enough to catch up with the gasoline car. And the question here we want to answer is, what are the candidate materials that allows us to actually catch up with the gasoline car so that we can completely safely phase out the polluting energy resources? And not only that, another problem we have to face in electric vehicles is about the charging time. Even with the current technology of Tesla fast charging car, we need to wait about 15 to 30 minutes for a full charge of the car, as compared to 1 to 2 minutes in the gasoline vehicles, where we can just quickly fill out the tank. And this is the reason why a lot of people are worried to use electric vehicles to drive for a long-range trip. And this is why it's our quest to find a better material for our battery. And the problem is there's no way for us to know the performance of the material except for building the battery and test it out. And today, we are focusing on how to build a better batteries. And the very first step is to find the actual material. And this leads us to the periodic table. And most of us are familiar with it. As we can see for the periodic table, there are only 118 elements so far identified on the table. And from the first sight, we might think that, yeah, it might be easy for us to test each and every one of the elements out to find out the best materials. But materials, especially materials combinations, are numerous. Take lithium, for example. If we want to build a battery based on lithium, we have a lot of different combinations as we mix and match all the different elements together. The same case is true for the zinc air battery, which is another good candidate for green energy storage devices. Not only that, when we look at the different components of the battery, for example, the electrolytes, there are thousands and thousands of different combinations we can use. And these are only the tip of the iceberg. And finding the best materials combination for our battery is like finding a needle in the haystack without any map. And here we stand today. We try to come up with the battery material from all of these combinations, and researchers have to test them one by one. And from Mariana's talk, we know that doing research on battery testing is very tedious. And first, we have to come up with the proposal for the materials. And only after that, we can synthesize the raw material. But on this stage, we have to make sure that the raw material is stable enough and pure enough for us to test it. And only after that, we can use the raw material to build one component of the battery, for example, the electrode, to test its performance. And only after rigorous testing of the electrode, then we can build the actual battery and know its performance. As we can see in this simplified diagram, it takes months just to test material. And I bet most of the researchers sitting in the audience will agree with me about the struggles of doing experimental work. You have to overcome the trials and errors while trying the different concentration of materials. The case where there's downtime and breakdown of your equipment, you have to wait for it to be repaired. And also lining up just to use a very specified equipment to test the property of your materials. Using these long and tedious experimental procedures will not allow us to catch up to the ever-increasing energy demand, as Mariana has been telling us. How can we ever be able to design a better battery fast enough to allow for a sustainable future, as we are facing global warming right now, and we only have such a limited time to overcome it? And therefore, here in recent years, we have been trying to replace all of this experimental work with computer simulations. And theoretically, we would think that computer can calculate it very fast so that we can test the material's properties very rapidly. But in actual case, computer simulation is so intensive such that even if we are using supercomputers, it takes as much time for us to simulate a material properties. And therefore, in Kirk's Bevan group, in our group, we try to find out the way for us to simplify and increase the efficiency of computer simulations, so that this allows us to do rapid material testing, and the researchers will be able to have a guideline of which material might be the best for their batteries and just focus on those materials in their research. And here, we learn two things. Is that computer simulations help us to accelerate the rapid material testing so that it helps researchers to come up with the best material. However, the second thing is computational method is very intensive and it takes a long time to perform. And this is why the talk we have today, we want to learn how to make computer simulation more efficient. Before we do that, we would first have to understand how computers simulate the energy storage devices. And in today's talk, I'll focus on supercapacitors, which is a hybrid between battery and capacitor characteristics. In a supercapacitor, we can see that it consists of a metal electrode submerging in an electrolyte solution. And in the electrolyte solution, there are charged ions floating around. As we are charging the supercapacitor, we are essentially stepping the potential to introduce electron into the system. And the presence of electron will cause electrostatic interaction with the ions. And this causes some movement in the system. And the movement of the ions in the electrolyte is the charging current that we detect in our supercapacitors. Continuous charging of the supercapacitor means that there is the continuous movement of the ions and translate into the charging current. And how the computer simulates this phenomena is by calculating and computing each and every movement of the ions frame by frame. And this will produce the data points to mimic the actual phenomena. This is very similar to how we are making movies by using different frames. Here is an example of a dancer, a 9-second clip that consists of 111 frames. Imagine if you were the artist and you were to produce this piece of art. You would spend 1 minute to draw each of the frame. And therefore, in total, you would spend at least 2 hours to produce the entire 9-second short film. This is the reason why our computational simulation is very intensive, is that we spend so much time computing each and every frame of our system, such that it takes such a long time to finish the entire simulation. And therefore, we have an idea. Wouldn't it be better if we can skip some frames strategically, but still be able to simulate the entire system? As we focus on this dancer analogy, we can see that the first 3 frames are so close together with each other, such that the actions did not differ much from each other. Therefore, we can safely say we might be able to skip every second and third frames. Instead of simulating a very small time step of 1 frame at a time, we would be able to skip and simulate 3 time steps at a time and eliminate the frame in between. This lessens our work, but still we are able to produce the dance very nicely and accurately. And thus, we can enjoy the same dance with only 1/3 of the work. But if we were to skip too much, we would see that this did not really capture the physics as well. And it would be something very chaotic. And we can never enjoy it anymore. And here, we learn 2 lessons. First is that if we want a very accurate result, we use small time step. But the simulation and production time is very long. And if we use a very large time step, yes, we can increase the simulation to be faster and faster, but we lost a lot of details in between. And this is the same in our computer simulation as well. If we use a small time step, it is slow but accurate. But if we strategically skip some points in between, we will be able to replicate the result but using less work to do. But if we were to skip too much, this is where the analogy of the dancer breaks down. If you were to produce the dancing movie, the artist knows what frames come after one another, and he knows the future. But this is not the same with the computer simulation. The next frame of the computer depends on the data and calculation you have in the previous frame. So if you skip too much detail, you will get something very chaotic, and therefore we have a lot of noise in our simulation. And we can never replicate the actual physics of the system anymore. And so the question here is, how much of a time step is actually the optimum time step for us to capture the physics accurately using lesser work? And as we want to answer this question, we go back to the system that we simulate. In this system, when the computer calculates the physics frame by frame, we are actually tracking the movement of the ions in the electrolyte. And therefore, this gives us an idea that we can determine the time step based on the velocity increase in the ions movement when you introduce the electron. So conventionally, researchers try to come up with a very accurate result for their research. And therefore, they push the time step into a very low number. And this is the result that most of us might get. Here we see there are 2 regions in this graph. The region separated by the green triangle. On the left side of the triangle, we can see that the time step that we are using is slightly larger than the velocity. And therefore, we might be skipping too much that we miss some details in between. And therefore, there might be some inaccuracy at the beginning of the simulation. But at the second part of the simulation, we can see that the time step we use is very small compared to the velocity. So we are essentially tracking down every minute movement in the electrolyte that we are able to recover the stability of the system. But the small time step will result in a very slow simulation. So the next step for us is to how can we come up with a better and faster simulation? The very direct answer is to increase the time step, but this is not what we would expect for the result, because this is chaotic and noisy. As we can see, if we have a time step larger than the velocity, we have a fast simulation, but inaccurate. Here again, we learn two lessons. First, we want to maximize the time step so that we have a fast simulation. And second, we want to keep the time step below the velocity line so that we still capture the movement of the ions in the electrolyte enough so that we have an accurate simulation. So here in our research, we propose a third solution to this situation. So in our lab, we try to use automation to compute the time step so that it varies along with the velocity curve, just to keep it slightly below it. And this is the result that we got. If we keep the time step slightly below the velocity curve as it plateaus, we got a very fast simulation with the accuracy all throughout the whole spectrum of our test. So here we can see that if we want to simulate the energy storage of the supercapacitor, we have a method of using the traditional low constant time step. But this results in a slight error in the beginning, but very slow simulation of 30 hours per run. By using our improved method of varying time step, we can reduce the simulation time by 1/3 of what we used to have, but still maintain the accuracy. And the success of this research allows us to do a rapid material testing instead of having a very intensive and long simulation time. The optimized time step will reduce it by 1/3, but still keep the accuracy. Apart from the time step that I mentioned in this talk, in our group, we are also trying to figure out how to efficiently simulate and calculate the electron in the system, which further reduces the computational time. And also how we can efficiently calculate the math and matrix operations in our computer simulation, which further decreases the time to a very realistic realm where we are able to do rapid material testing to come up with a best candidate for our batteries. Not only that, by having an optimized computer simulations, we will be able to do parallel simulations, which further increases the capacity for our testing to screen off all the materials that we have been seeing so far and the materials that we haven't been exploring in the periodic tables. Here, we can see that computer simulation gives us the power to rapidly screen off the material so that we are able to catch up with the increasing energy demand. And at the same time, this allows us to have a better idea of which material is suitable for us to design a more sustainable energy storage devices. And therefore, a prosperous future that we all live in sustainable condition, where everybody have a chance to drive an electric vehicles, and every house powered by solar farms and wind farms will no longer be an empty dream, but it will be our reality. Thank you very much, and I would like to thank my supervisor, Professor Kirk Bevan, sitting at the back, and my research group member for their continuous support. And I would like to thank TISET for this opportunity. And thank you very much for being part of us tonight.
Thank you, Yee Wei.
Thank you.
So we have time for a couple of questions for Yee Wei. Yes, please. And please use the microphone for the questions so that the video recording will hear it.
Thanks a lot. It's Michael Johnson from Siemens Canada. So You know, you inspired me tonight to think about how good is good enough. So,
Yes.
so how do you know, what are you looking for when you're optimizing this way that you do the simulations, and how do you know you've gone to the right level?
Yeah, for our computation of the charging currents, we use an exponential fit for the decay of the current, and we set certain limits for the tolerance level. And from there, we can see how we can compute the actual optimized time set for that frame of the computation.
Any other questions?
Yes.
Avram Goldman from Pratt & Whitney, Canada. Thank you for this excellent talk.
Thank you.
The simulation method sounds like it might be applicable in other fields. Is there some way you could, say, brainstorm with your other counterparts and see if there's other fields that you're not familiar with where it might be applicable?
Yes. So in our group, we have simulations in various fields. I am focusing on supercapacitor, and my colleagues focus on fast field modeling, and some focuses on hydrogen fuel cells, and some even focus on DFT simulations. So we have the simulation for every single field that we might be able to tune our simulators to the specific applications. Thank you.
One last question,
Yes.
please.
Thank you for the talk. And I was wondering which kind of simulations you are doing, but you answered that one. You are doing a DFT. Then it seems that in your simulations, the time scale is important.
Yes.
But how do you translate that in DFT computation, and how do you manipulate the time scale to accelerate your simulation?
So for my talk today, the specific case that we apply this time step optimization is in the continuum model, which is far away from the DFT. So in the DFT, we have different issues that we have to tackle, for example, the correlation exchange terms. And these are the different computational challenges we have to overcome in order to optimize those systems.
Great, thank you. Well, let's thank Yee Wei again.